Okay, so thanks, Tom, for the introduction, and also thanks, Percy, for the introduction, the background, and the advertisement, so I can carry on to provide the detail. And so today I will talk about Riemann Hilbert approach to the perturbation of orthogonal polynomials and the several applications. Okay, so the topic of this conference is random matrices and numerical linear algebra. So from our perspective, the connection is via orthogonal polynomials. Okay, so this is the point I want to say. Okay, so here is the outline of the talk. Okay, so I'm trying to make it accessible to a more general audience. So I will first of all discuss what is orthogonal polynomials in case you don't know too much about that. And then I will give you what is the mathematical problems we are interested in. And then after that, I will go back to talk about, okay, so providing more details. So based on Percy's introduction, okay, so why this is important from the perspective of numerical linear algebra. And then I will briefly, okay, so try to introduce another approach, okay, which is by Elliot and Tom. And so they have another approach to handle a certain class of random matrices. And then I will try to introduce our approach, which constitutes two components. The first one is the Riemann Hilbert approach. The second one is the part from random matrices, okay? And then in the end, okay, so in addition to Percy's takeaway message, I will provide another two takeaway messages and also two open problems, okay? So by the way, I'm also a statistician like Joe, so I'm trying to also try to think about something, from an applied perspective. So, okay, so what is orthogonal polynomials? Okay, so if you have a measure on R, so okay, so you can always define the polynomials, which is monic polynomials. Basically, the coefficient is 1. And applying the Gram-Schmidt process, you can always get the orthogonal polynomials. Okay, the coefficient may not be 1 in this case. Okay, so and then you can just normalize it and go the orthonormal polynomials. And another quantity associated is the Cauchy transform. Okay, so if n equals to 0, it's closely related to the Stieltjes transform in random matrix theory. So in addition to 1 or 2 pi I. Okay, so you can say so they are connected with random matrices via these quantities. Okay, and another remarkable relation is the 3-term recurrency formula. Okay, so so they try to provide a way to describe the coefficient of these orthogonal polynomials. And so they're actually, if you try to rewrite this formula, you can find a Jacobi matrix, which is the mapping of how you can describe these orthogonal polynomials. Okay, so then, okay, so what is our questions? Okay, so now suppose I have another measure which is new, so which can be either a perturbation or a random measure which is trying to approximate, so the given measure. And so our question is trying to understand, okay, so now I have two measures, okay, I can construct two sequences of orthogonal polynomials, okay, so what is the relation between the two sequences of orthogonal polynomials, okay? So if mu and u are close, or in some sense they are close, and that this closeness can be transferred to the closeness of orthogonal polynomials. If this is true, in what sense? Okay, and in many cases, for example, if nu is from the eigenvalue or distribution for random matrices, it could be random. So therefore, in this case, you will have another parameter which is big N. Okay, so small n is a degree of polynomial, big N is a dimension of the matrix. Okay, so how far can we go in terms of small n? Okay, can we let small n diverge with big N or just fix N? And finally, okay, so we want to look at, okay, so if these two are close, what is the distribution? Okay, what's the second order factorization? Okay, so we are trying to answer question 1 and 2 in a relatively general way in terms that we don't impose any random matrix model. Okay, but for 3 and 4, because we are talking about a asymptotic distribution, so we need to have a model. Okay, we will import given some random matrix model to discuss. Okay, so how large the small n can be in terms of big N and what is the distribution. Okay, so this is what we're trying to do. Okay, so we of course, to fully answer these 4 questions, so we need to spend more time, and we are trying to give you some ideas. Okay, so how one can do this. Okay, so first of all, why we care about orthogonal polynomials? So why people from numerical linear algebra especially, okay, they care about orthogonal polynomials. Okay, so one reason is from the conjugate gradient algorithm. Okay, so And Percy has mentioned a little bit. Okay, so this is basically the mathematical formulation for this algorithm. Okay, so this algorithm aims to solve this very simple linear system. Okay, you have a big N times big N matrix. Let's say it's a permutation matrix. Okay, and you are trying to estimate this X given a unit. I mean, so given a unit vector B. Okay, so B is deterministic. Okay, so W can be either deterministic or random. Okay, so and so then the CGA actually trying to estimate this X via this optimization problem. Okay, so this W norm is essentially the quadratic in terms of W. Okay, and so how this is connected to also polynomials. So this is connected with the so-called eigenvector empirical spectral distribution. Okay, so this is different from eigenvalue spectral distribution. So now I have a W matrix that says it's random. Okay, I can compute its eigenvalues, which is lambda I. I can also compute its eigenvector, which is ui. Okay, so I will project this ui to all these bi's. These are my weights. Okay, I'll apply all these weights to the eigenvalues. Okay, so then I get another spectral matter, which is called eigenvector empirical spectral distribution, which is VESD. Okay, so for the eigenvalue distribution, all these weights are 1 over n, which is they are equal. I mean, so weighted. Okay, and so with this kind of measures, I can also create a sequence of orthogonal polynomials. Okay, so even though it's discrete. Okay, and then so for this CGA, I'm interested to look at its performance. Okay, in terms of the residuals. Okay, so Xn is just the estimator getting from the nth iteration. Okay, from CGA, and then so there's a result. Okay, so if you first of all take the Jacobian matrix by using the VSD and then do a Cholesky decomposition, okay, which you get, which is a L of nu, and then the residuals can be explicitly write down into a product of all the entries of Cholesky decomposition. Okay, you can say the orthogonal polynomial are essentially collected to this CGA, so using the VESD. Okay, so there exists a connection. So this is actually the motivation we want to study this problem. And so can we really do this? Okay, so first of all, I want to show the result, then I will come back to explain more. Okay, so the answer is yes, we can do it. Okay, so for different, these are corresponding to different random matrix models. Okay, so all these things we are trying to, all the green lines are just the empirical one, the red ones are just the prediction ones. You can see we can do it pretty well. Okay, so I will explain how can we do this. And before going to our approach, okay, I want to first of all introduce another approach and which can handle, which is so this kind of approach is actually basically trying to understand the universality of the CGA algorithm. Okay, so don't forget we are trying to understand the orthogonal polynomials. As a consequence, we can study this algorithm, but there already exists a method to study CGA for certain random matrix models. Okay. So the model, so they studied, so it's just the simple coherence matrix, so which is X transpose. Okay, so X is a big N times big M matrix. Okay, so entries means 0. So its I the entries is normalized by 1 over n. Okay, and so they assume that the moment, so they assume, they have enough moments. Actually, they assume all the moments exist, and these are, and in addition to that, the first 4 moments have to be the same with the Gaussian random variables. Okay, and so there's a big advantage about this approach that they don't provide any assumptions on the ratio of n over m, because for CGA, if the smallest argument is too small, it can be a trouble. Okay, especially when n over m equals to 1, okay, which implies the smallest argument is too small. But the advantage of this approach, because they can compute everything explicitly with Gaussian, so they don't have any assumption on this ratio. Okay, and then actually they studied 2. So this kind of algorithm, one is CGA, the other is minimal residual. So they all have the similar formulations I showed before. Okay, and they studied both the first order and the second order statistics of both the residuals and also the errors. And this is one of the graphs they can show. Okay, and I don't know why okay, so this is a prediction. So something disappear here. So so the matches with the simulation part. Okay, and so there's another line, which is the green line, basically means that, okay, so fix any epsilon, we can look at the halting time. They are also pretty concentrated on certain so iterations. Okay, this is their result. So what's the key ingredients in this method? Okay, so so their methods have two steps. The first step is trying to understand what is going on with the Gaussian case, and in the second step, so they are trying to utilize the local laws from random matrix and then to generalize to arbitrary so distribution. But the key part is trying to get an explicit formula for the Gaussian case, and the very important so ingredient is bidiagonalization. So for this invariant ensembles, okay, which is proposed by Allen and Joanna, so like 20 years ago. Okay, so so if you have a Gaussian matrix, so beta equals to 1 is real, beta equals to 2 is complex. You can always find two matrices, which is invariant U1 and U2, so that you can have this very nice bidiagonal form, and all these entries are independent, they are chi-distributed. Okay, so and then based on that, you can just basically multiply this U1, U2 matrix. You can see in the very end, the study of this W matrix reduced to a very nice tridiagonal matrix. Okay, and all the entries, the distribution are known, and for each yjk, the entries are independent, so you can just do it. And this representation, they also show that, okay, so this if you look at this yjk transpose, they are directly related to the Jacobi matrix, associated with the orthogonal polynomials, and they also have to, via the Lanczos iteration, of course, you have to use the invariance of the Gaussian distribution. Okay, this is the key parts. And as I mentioned, okay, in the first step, they compute the asymptotics for the residuals and errors, and it's using these Gaussian ensembles, and because for chi-distribution, you know everything. Okay, so then you can just compute it. In the second step, okay, so they can apply this comparison strategy, to generalize the Gaussian to any general distributions, assuming the first force moment are matching. So why you can do this? The reason is because, okay, so essentially all the entries in the Jacobi matrix, they are smooth functions of the moments of the VESD, okay, and using the Hankel determinants, okay, the standard definition. And then all these moments can be characterized by the zeroth order of the Cauchy transform, which is the Stieltjes transform, okay. Then you can see that in order to compare the Gaussian with the non-Gaussian case, you only have to compare the Stieltjes transform with the Gaussian and non-Gaussian. Okay, that is the case. So you do that, the local law will come in. Okay, so that's the idea of their approach. And so there are several advantages and also limitations of this approach. So for advantage, as I mentioned, okay, so the calculation for Gaussian are so explicit. Okay, so they don't require any assumptions on NOM. Even though NOM goes to 1, they still work. Okay. And so formulas are really, really simple. Most of the result only depends on the ratios of NOM, and so the implementation is really nice. Okay, so you don't have to write too much code. Okay, and but on the other hand, there are many limitations. For example, in this case, even for the simple covariance matrix, if the covariance is not identity, even in the Gaussian case, the method fails because you do not have this nice bidiagonalization procedure. Okay, if it's non-Gaussian, of course it fails. And also on the second is that, okay, so because of the comparison procedure, they have to make sure the first 4 moments match. But however, in the random matrix society, because this kind of analysis is average, is mostly like a bulk analysis, we believe only the first 2 moments matching is sufficient. Okay, if you have 4th moment, probably the only thing changed is the variance part. Okay, so therefore, so we're also trying to generalize, so in terms of the second perspective. And then the previous approach, requires the iteration number is fixed. Okay, so we are trying to let the k diverge a little bit. Okay, so in that sense, you can see that we really need some tools which are less sensitive to the isotropic Gaussian assumption. Okay, so this is a key idea. Okay, so now let us try to describe our approach, which there are 2 components. The first part is the Riemann Hilbert part, and the second part is just a comparison part. And so for Riemann Hilbert part, okay, so so as I mentioned, our goal is actually trying to understand the orthogonal polynomials, and consequently we can study this numerical algorithm. So the reason we are trying to use this RHP approach is because there exists, like 30 years ago, there exists a very nice, so RHP approach trying to show us, okay, so how can we represent these orthogonal polynomials in another way, okay? So I can define this matrix valued function. You can see it contains all these orthogonal polynomials. It's Cauchy transform, and so on and so forth. This gamma actually the normalized constant for this orthogonal polynomials. Okay, and under suitable conditions, I mean, so they can show. I mean, so this y plus is essentially you are trying to approximate this y from the upper half plane. Y minus is just from the lower half plane. Okay, so they can show that these two parts are connected with a simple jump condition. Okay, jump condition. Let's assume first of all this mu has a continuous density function. Okay, and then okay, so because you see that pi of n, the leading order is a z of n, so therefore I mean so you need this kind of normalization, I mean so conditions. And if you have a measure with a continuous density function, the first three conditions will constitute a Riemann Hilbert problem. Okay, but now we need more for our case because in the end we will have many discrete measures, so therefore we can modify this a little bit by adding these conditions. Therefore, if you do have some discrete mass point, and the first four equations will constitute the new Riemann Hilbert RHP. Okay. And so now I will try to give some assumptions, but I will believe that our results can go beyond this assumption, but this is only for technical convenience. Okay. So we consider that, okay, so for the mu measure, okay, so it has two parts. The first part is a continuous part, okay? So we assume that, okay, so we have a certain square behavior, okay, so near the edges, okay? You can see, I mean, so you can see there, we're already trying to talk about random matrices because the square decay behavior near the edges, okay? And we also, for flexibility, we also add a certain mass point, okay? And this P can be 0, but the G should be greater or equal to 0. At least you have one interval serve as a component, okay? And so previously when we defined this RHP, okay, all this they must be outside the support of mu. I mean because we're interested in all all these spectral parameters, so we have to modify this a little bit. Okay, so we just simply introduce this new so quantities which can contain all the complex values z. Okay, so in all the complex planes. Okay, and I mean technically, okay, so we can use this check head by n, and all these kind of things are just a constant. Okay, you can think about it as one in most of the cases. Okay, they are just a technical issue. And so now, okay, so we started. I mean, so we will working on this specific, I mean, so matrix valued functions. Okay, yeah. Oh, Cj's are potentially some point mass. For the intervals, we have A1, A2. So by different intervals, their gap should be, I mean, separated. Okay, it's well separated. Yeah. No, I mean, we are outside the gap. Okay, yeah. So you can think about these Cj's are outliers. They are just separated from the bulk of the spectrum. Yes. So the main reason is because we have a spectrum model. We can study that for the spectrum model if we introduce this one. Yeah. And then based on that, we will, because we're interested to look at the closeness for different two measures, we will introduce a new quantity which is xn. Okay, so they are essentially the first part for, I mean, so which is the inverse of the mu part and then multiplied by the new part. Okay, so I mean, so ideally, if this mu and nu are close, I mean, so this xn should be very close to identity matrix. Okay, and then we can show that. Okay, so this xn, we can find another RHP for this xn, and then this is a jump condition. Okay, you can see that. Okay, so the only thing which is involved in this jump condition is actually the difference of the Stieltjes transform of the two differences. Okay, so therefore you can see that. Okay, so in order to study the two different sequences of orthogonal polynomials, their difference can be potentially quantified by the difference of their Stieltjes transform. Okay, so this is what I mean. So in what sense they are close? Okay, in the sense of Stieltjes transform. Okay, and then we can really show our first result really show that. Okay, so under suitable conditions, I mean, so we can have such a expansion. Okay, I mean equal to identity. This is the first order correction. This is the high order correction. Okay, so this MN matrix we can also write it down, and so I will try to explain, okay, so what is the magnitude of this MN later, okay? But I mean, so you can see that, okay, so we, on one hand, we don't want this date too far away from the real line, right? Otherwise, it can grow exponentially. And on the other hand, we don't want to on Z to be too close to the real line because this Stieltjes transform will blow up. Okay, because the immediate goes to 0, the Stieltjes transform will blow up. So there's a trade-off between these two quantities, which that's the reason we have an upper bound for the lowercase n. Okay, so I will explain this perspective, okay, so in a minute. Okay, and in fact, okay, so because these YNs are directly related to this orthogonal polynomials, you can just write it down. Okay, so this is a general formula. Okay, so I mean, so this perturbed part mu is close to mu. Okay, so you have a random, okay, so arrow here and also a high order random arrow. Okay, so this is a condition. And in fact, okay, if you know mu very well, you can do an asymptotic expansion for the orthogonal polynomials associated with mu, and then you can get a more nicer formula. Okay, I don't want to explain all these quantities here. They are essentially come from the asymptotic expansions for the orthogonal polynomials. I mean, so they are related to the theta functions. I mean, so for that part. So I mean, so you, if you're interested, I mean, everything can be computed explicitly. So yeah, one point is that, okay, even though it's really complicated, but everything can be computed explicitly via numerical computations. Okay, at least for general class or random matrix models. Okay. And and another thing is that many quantities only depends on the support of mu and let alone the density of mu. Okay, so some part depend on density, but many only depends on support of mu. Okay, I will explain why this is important, because in random matrix theory, okay, so there exists a theory to help you compute the edges, I mean, so the density, okay, without knowing the whole picture of the distribution. Okay, and after knowing this perturbation theory of the orthogonal polynomials, we can come back to study various, I mean, so numerical algorithm like a CJA, like a track space decomposition, or the Lanczos iterations. Okay, so many algorithms we can study. So, for example, for the non-perturbed version, okay, so I mean, so you can expand the orthogonal polynomials and get a formula for the arrow. Okay, and if for the perturbed version, you can just get a similar formula as well. Okay, so I don't want to explain. You can see that, okay, for the key part for this one, okay, it depends on the theta function of a certain Riemann surface, and depends on the edges of the support and also the outliers of the support and some other quantities, essentially from RHP. Okay, but everything can be computed explicitly. Okay, so with numerical calculation. Okay. And so I will give a very simple example to show how our work coincides with many works done by Percy and Tom and Elliot. Okay, so suppose we only have a single support. I mean, in this case, all the theta functions is just a one. So I mean, so you don't have this kind of things. They are just a one. Okay, and then in this case, okay, so if you look at the ratios between the two residues, okay, so they have a very simple formula. Okay, so exponential to g to the g0. G is just if you are familiar with RHP, it's just exterior green functions. I mean, so when you're trying to do the asymptotic expansion. Okay. And we can further show that, okay, this quantity is essentially very, very simple, only depends on the edges of the support. Okay. And then, okay, in the case, if you only have look at the standard V-short case, in the case that the edge is just 1 minus the square root of d square and 1 plus square root of d square. In this case, I mean, so E negative G0 is just a d. It's exactly the result. I mean, so Percy introduced. I mean, so minutes ago, and this is also coincides with the paper. I mean, so in Elliot's paper. Okay, so this is a very simple case. Okay, And so then I will introduce the second component, and basically this is the random matrix part, because we are trying to understand the third and fourth question: what is the distribution? Okay, and how far we can go in terms of okay. So what is the local loss of random matrices? Okay, this is a so this there exists lots of literatures in this area. Okay, so for lots of random matrix models, that's called a W. Okay, the W can be very general, like a big matrix and like a simple covariance matrix, like free convolutions, and as many as you can. Okay, so you write down the resolvent. Okay, so for complex value Z, and then take the quadratic form. Okay, then it's really close to expectation, and then with a high probability. So this notation is with a high probability, and then the error can be computed explicitly. Okay, what is this? Is mu, and mu is the C's transform of the limiting distribution of W. Okay, and in many cases, this expectation can be computed explicitly. Usually, it only depends on the C's transform and some detailed information of the random matrix model. Okay, so actually there are many different matrices. I mean, so their local laws have been derived, especially by the group of Erdős and Yao, and so you can take any matrices you want. I mean, once they satisfy this local law. Okay, and so then based on this local laws, then we can see why we have this upper bound. Okay, so on one hand, I mean, for the VSD, okay, the best local you can see is just 1 over square root of n times eta. Okay, you can think about the eta is related to n. Okay, so because we want to control the imaginary part. Okay, and then you can also show that the m part is infinity norm can be controlled in a certain exponential way. Okay, in a certain exponential way. Okay, combine these two. Okay, the best thing we can do so far is n to the power 1 or 6. Okay, but I mean I will show it in the figure. We believe that so once n is much smaller than big N, the result should be true. Okay. So, but at least so far we can do till here. Okay. And okay, so I will give a case study. Okay, so I will focus on because I'm a statistician. I mean, the most important model is the general or spiked covariance matrix model. Okay. I mean, so yeah. Oh, capital MN is just the size of the matrix. It's a big M times big N matrix. Okay, so here, I mean, so this is my X matrix. It's just a big M, big N times big M. Yeah. Oh, this big M. Oh, sorry. Okay. So this is involved in here. Okay, this is involved in our first order correction for the Riemann Hilbert problem. Yeah. Okay, and this is the definition. Okay. Yeah. Sorry, there are two big M's. So sorry. Yeah. Okay, so I mean, I will do a case study for this. I mean, so celebrated. I mean, so covariance matrix model, and again, so previous. I mean, so this sigma equal to identity. Okay, so here I can allow sigma can be quite general. Okay, and so I basically what is the regular assumptions? Basically, the assumption ensures that so if you look at the limiting distribution for this W, it has a square root behavior. Okay, I mean, so so that's the assumptions we have to impose from sigma, which is relatively standard. I mean, in the random matrix literature. Okay, and then this is our result. Okay, so for any fixed Z, okay, so we can try to look at the distribution of the two sequences of orthogonal polynomials. Okay, so by properly normalizing it, this big Z is a constant. Okay, which depends on this small z and also mu. Okay. It's a asymptotically normal distribution with 0, and the variance contains two parts. Okay, the first part is V1, which is always order 1 term. Okay, the second part is V2, so which relies on the false cumulants of the entries of the random variables. Okay, and the V2 will vanish if your iteration go further and further. Basically, this basically means that the universality becomes more transparent if you do more and more iterations, which are kind of satisfying iterations. Okay, but if for fixed small n and so the variance will depend on false cumulants of the random variables. Okay, and now I will try to provide some simulations. Okay, so I mean I already showed the first probably I will go back to show the residual part. I mean, so again, so this is I mean, so the first part we look at the residuals. I mean, so for CGA, okay, and for the first part, okay, so we the limiting distribution only have one component, okay, you only have one the support only have one interval, okay, you can see that there's like a straight line, okay, straight line. In the second case, okay, the limiting distribution have two intervals. They are these two intervals are separated. If you look at this they have a certain like a periodical phenomenon. They have a certain oscillation. Okay, you can see that. Okay, so even though I mean so the theory, okay, so I mean so quite general, but if you look at pictures, I mean so they are quite rich. Okay, so it depends on what is the true what is your true matter. Okay. So and then we can also study okay, so other I mean so numerical algorithms, and the one is let's first start with the Lanczos I mean so tridiagonalization, which basically contains the coefficients of the orthogonal polynomials, and the blue part are just the diagonal terms. So diagonal terms, I mean, so involved with K. Okay, you can see that. Okay, so I mean, so there are already some blank lines which are the empirical, are blue are just the predictions. Okay, so the matches pretty well. And so I mean, and the right part are just the off diagonal terms. Okay, and then you can, based on this Jacobi matrix, you can do Cholesky decomposition, and we find similar results. Okay, so I mean, this is the simulations, and so I mean, so this is also the case. We have two intervals for the support. Okay, and then so you can see, you really see very interesting features. Okay, and so now I will give some takeaway message. Okay, so the first message is that, okay, so in the random matrices and society, okay, so people have been working on eigenvalues for many years, and you can see from here, okay, so probably I mean, so people should also spend more time on eigenvectors, because in numerical linear algebra society, mostly you see is eigenvector instead of eigenvalues. Okay. So the second is that, okay, so the establishment framework, especially the IHP part, is very general. Okay, so here we study CGA, and of course, I mean, so people care about the conditioning, which is a deflated CGA. Okay, so and we are, ongoing work with Tom, we are trying to study one type of this CGA. Basically, assuming that some of the eigenvalues are very small, how can you impose? I mean, so how can you modify it? All the CGA works, and it turns out that the only part differs is the random matrix part. Then I mean, so the IP still works. Then you have to work on the new random matrix model, derive the local laws, and then you can get the results. Okay, so this is this, you can see this is the general. I mean, so even though these two components are connected, but they are also relatively separated. Okay, so you can try to reduce the problem. Once you have a nice random matrix model, then you can just work on this approach. Okay. And in the very end, I will just discuss this. I mean, so kind of two open problems. The first one is as I mentioned. Okay, so I will take the Cholesky factorization as an example. Okay, so for K, okay, so TLK equals 25. I mean, so everything looks very good. Okay, but if you say if K goes deeper, okay, deeper and deeper, okay, you can see that our prediction are no more accurate. Okay, and even so, it seems that even the diagonal part seems to be more accurate in the off diagonal, but apparently something happens here. Okay, so therefore, I mean, so it's a question. Okay, so if your K at least is comparable to N, okay, so what can we do? Okay, and finally, so this is not even an open problem. So this is essentially my own interest, because whenever I have to do something, I will ask myself, can we apply this result to statistics and try to convince the statisticians they are actually useful? Because I mean, usually when I give this talk, people ask me why I never heard of IHP in statistics society, why this is useful. Okay, so I will show an example here. And hopefully, I don't know why this is the case, but I try many different cases. And then this is one thing I think I can convince statisticians, okay, in some sense it's useful. Okay, so in statistics, people, the one important part is doing inference. Okay, so you are trying to test whether something is equal to some given something. For example, suppose you observe a sequence of a multivariant Gaussian, okay, so vectors. I mean, their mean is 0. They have a certain covariance, which is called population covariance matrix. Okay, so and in many cases they want to check, okay, so whether this sigma equal to some, let's say, some given matrix A. Okay, in my simulation later, I will assume this A has two. I mean, so has a point-wise 1 and 3, the other one at 1. Okay, so half of the 3, half of the 1. Okay, and so of course, I mean, so in order to study whether it makes sense, we will consider certain alternatives. Okay, so one alternative probably is something like, okay, whether it differs from A by a finite rank deformation, or a 4-rank very small 4-rank deformation. These are two widely considered. I'm not sure whether it's widely considered, but I found them in the literature. Okay, so so this kind of problems in high dimension have been studied. I mean, so for a few years, and then you can see there are many. I mean, at least there are 3 very. I mean, so very famous, I would say. I mean, so testing method trying to test whether this sigma equals to A. Okay, so one is trying to use linear spectral statistics. Basically means that they are trying to look at to normalize the trees of the eigenvalues of the simple coherence matrix and use it as a testing statistic. And or they can use the likelihood ratio statistics. And finally, there is also a third testing method, which is especially designed to test the first alternative. Okay, and which is called a Cholesky statistic. Okay, so I don't want to explain what they are, but they exist in literature. I mean, okay, so there exists method. Okay, so now I'm trying to say, okay, so how about I utilize something from my calculation? Okay, because I know the distribution very well, I'm trying to use the diagonal entries of the tridiagonal decomposition, trying to do the testing. What do I mean? For example, under sigma equal to A, I know the distribution. If the sigma is different from A, for example, in the following 2 senses, I will have another distribution. Maybe the variance are different. Okay, so you can imagine the larger the D, the larger the epsilon, the more easier the problem is. Okay, I say, okay, so how this different methods works. Okay, so I'm trying to study the power. What is the power? Basically means that suppose your sigma is not equal to A, so how can you able to reject the null hypothesis? This is, I mean, roughly this is the power. Okay, so you can say that, okay, in the first setting, basically it's just the low rank deformation setting. Okay, so it seems that all methods works, but in terms of power, our proposed method seems to be better than the rest of the 3 methods. Okay, and similarly for the other one. For the other one, means that the Cholesky fails because, I mean, so this is a 4-rank deformation. Okay, in the final settings or method, I mean, so also perform all the methods, I mean, so existing in the statistical literature. Okay, so this is a purely empirical observation. I don't know why this is the case, but at least hopefully, I mean, so for some statisticians, they are convinced. Okay, so I mean, so I'm not trying to use harder statistics to do harder mathematics to do statistics, but this is a case we want. We do see improvement. Okay, so this is that's all I want to talk about, and thank you for your attention.